Okay, our first speaker is Martin Fencl. He is a researcher affiliated at the Czech Technical University in Prague. He is an expert in urban hydrology and hydrometallurgy. His research focuses on innovative methods for measuring rainfall using commercial microwave links and their use in urban hydrology. Within the OpenSense action, he is in particular the grant holder scientific representative of the action and also co-leads working group 1, which focuses on data management and standardization. Okay, and if Martin is here, the floor is yours.
Great. So good morning. My talk is about basically now more than a decade of research we did on a topic of using commercial microwave links in the context of urban stormwater management and urban drainage modeling. And I would like to give also credit to our former PhD student Jaroslav Pastorek and Vojtech, who is also chair of this cost action, and we do this research together. Let me start with a short introduction to sewer system and like urban drainage. Sorry. Yeah, urban sewer systems are like really great technical structures which work very well for more than 100 years in Europe. They were designed in 19th century, as a response to the population growth in cities and sanitation problems, and it was very successful response. And in most of the European cities, we have like combined sewer system where sewage and stormwater is drained together towards wastewater treatment plants. And these systems have also, although they work very well from the point of view of end user, they have also some limitation. For sewage is mixed with stormwater, and even during moderate rainfalls, it overflows during to the receiving waters without any treatment. Wastewater treatment plant capacity is also limited, and efficiency is low during rainfall. And also, sewers are designed for rainfalls with return periods from 2 to 5 years. And sometimes when this is exceeded, we hear about sewer systems also in newspaper headlines. So these are kind of problems of these systems, and they are amplified by increasing urbanization, climate change, and also new chemical species like pharmaceuticals. And to fight with these monsters, we have to take some in-sewer measures like retention tanks or like real-time control, but also catchment measures like blue-green infrastructure, retention, some green roofs, or infiltration trenches, and so on. And to take these measures efficiently, we need to do planning, evidence-based planning based on well calibrated drainage models and high quality rainfall data. And this data is often missing at required quality. The problem with urban catchments, or the challenge with urban catchments, is that there is a high ratio of impervious surfaces. They are drained by sewers with combined sewers overflow, so there is a short time of concentration and very dynamic response to rainfall time space variability, or to rainfall dynamics. So this means that we need rainfall data with high space and time resolution. And on the other hand, we have in cities like many potential sensors, commercial microwave links, which are densest in urban catchments. We can get attenuation or rainfall data from them with resolution even lower than 1 minute. They measure close to grounds, and data is potentially accessible operationally. So there is quite nice potential for completing standard monitoring networks drainage model calibration and operation, and also for real-time control of sewer and wastewater treatment pattern, early warning, and so on. And our research is like having this like main research question is what is the potential of microwave links for urban rainfall runoff modeling, and how to properly process microwave link data. This is at the end quite complex, because if we like rephrase it as a goal, we see that we have here like rainfall information suitable for rainfall runoff modeling in urban catchments of different sizes, and we want to get this information from attenuation data of many microwave links with very diverse characteristics. And our research is about these three aspects and their interplay. We started to collect microwave link data basically, or collaborate with T-Mobile in 2012 and developed SNMP-based data acquisition system in 2013, which was tested first at a small catchment on 20 links, then extended to all Prague and 2 other cities in Czech Republic. Then for about 4 years ago, when we extended this data acquisition to the whole Czech Republic, or one half of it, where there is this one sub-network we collect. It's more than 2,500 links now. And we were also piloting 2 years ago a real-time supply of this data to water utility in the city of Olomouc with 100,000 of inhabitants. And I will talk here a bit more about like 3 case studies or 3 catchments. One in Prague, Letňany. This is this catchment where we started the data acquisition, and it's a small urban catchments where there are high requirements on rainfall data quality and resolution. Then I will say a few words about modeling in a larger catchment, which is like catchment of 1 or 2 trunk sewers in Prague, and then tell a few words about this experience with real-time operational and data-driven runoff modeling in the city of Olomouc. Just a few words about how we process microwave link data. We get attenuation data, like total loss, how link is attenuated by rainfall, and we need to separate dry weather attenuation from rain-induced attenuation, then correct for wet antenna, because antennas get wet and produce additional attenuation, then the path integrated attenuation. And when we separate this, we can convert it specific attenuation caused by raindrops along the path of a link to path average rain rate. And in urban catchments, there are many short microwave links. They are potentially very informative, but they are highly biased because of this like wet antenna, or we need to really like treat them correctly with wet antenna correction. And in all of these like studies we did, we basically evaluate the potential of microwave link for drainage modeling by comparing simulated discharge based on microwave link data with urban drainage model, comparing it to the observed discharge, and then quantifying the mismatch or the error. And we can also do this by feeding the model with some like benchmark data from rain gauges or radar, and compare how well we stand compared to standard observation systems. The advantage of this approach is that it's relatively easy to measure like discharge in flow in sewers. The disadvantage is that we mix together like rainfall induced uncertainties with the uncertainties of rainfall runoff model, with some structure deficits and parameter uncertainties. So just when we started, we were interested how good are microwave links when we use them in urban drainage modeling alone without any fine tuning. We started with this like catchment, which is well monitored. There are 19 microwave links. There are like municipal rain gauges nearby the catchment. I will just yeah, here we have like municipal rain gauges less than 3 kilometers from the catchment, and we also installed some rain gauges while covering the catchment. We have a flow meter at the outlet of this catchment. And in this case study, we were like simulating runoff for 2.5 years of data with the 6 events, and we were comparing at event basis simulated and observed runoff and quantifying like difference in the runoff volume and correlation. And we'll look at the results to check my time because yeah, when we look at the results, we see like that we're doing these simulations for each link separately and then like using all the links. And when we sort these links from the shortest to the longest, you can see that short links provide quite like biased volumes of runoffs on average, and longer links are unbiased. And in terms of correlation in this overall evaluation, it's more or less the same. And when we like average all the links except some with gross errors, we actually get the most robust results, and it's almost like comparable with this like municipal rain gauges. But it's interesting when we look at heavy rainfalls, we see like similar trend with the volumes, but we see here that that correlation is better by the short links, which are more like better covering the catchments and not extending far from the catchment. And what is interesting, I would say the most, that when we take this like mean of all the links, we get way better correlation when using this remote rain gauges. But we have still some like bias in this data, and we see actually a very similar picture also when we go to larger scale to this like trunk sewer in Prague, where we were doing like similar study with microwave links without tuning, and we are comparing it with rain gauge input and radar input and observed runoff. And again, microwave links are quite biased, but they have really good correlation, and their predictions are basically more robust than predictions from rain gauges. So we ask question how to reduce this bias, which is caused by the wet antenna attenuation, and if we can use like commonly available observations from urban areas. Like one idea is to use some like remote rain gauges aggregated to larger scales, and in long term they are like unbiased, but they cannot capture this small scale variability in the catchment. And we use these remote rain gauges to calibrate microwave links, and like and then we also try to calibrate microwave links with runoff data, basically by by minimizing the error between simulated discharge from microwave links and observed discharge. And we did this at the same catchment. And here you see like that we use only the links in this case which are inside the catchments or which best cover the catchment, and we optimize them based on really like remote rain gauge, not suitable for rainfall runoff modeling, based on these 3 municipal rain gauges, and also based on flow data. Again, we have like some 2.5 years of data, 23 calibration events, 23 validation events. And when you look at the results of microwave links optimized to flow data, we see that we obtain, actually here on the x-axis there is an observed runoff, on a y-axis simulated runoff, and the results are actually better than results from these 3 municipal rain gauges, and they're almost as good as results when we used these 3 benchmark rain gauges while covering catchment, so experimental rain gauges. And similarly, when we optimize to these three municipal rain gauges, the microwave links, and then use them as an input for runoff model, we obtain way better runoff estimates than when using these municipal rain gauges alone. And even when, sorry. Oh, yes, no problem with the pointer. Yes, I'm there. Okay, so even when we use only this like remote rain gauge, we get pretty nice, like almost unbiased rainfall estimates, or there is a 10% systematic errors, but very nice correlation and very low root mean square error. We also like we're interested in if we are able to model like uncertainty of our predictions, and that extended our deterministic model by some error model with time dependent bias and random noise, and used Markov chain Monte Carlo method to infer posterior distributions of this of this error model, and we were able to simulate like uncertainty bands which reflect how confident we are with our rainfall runoff estimates. And these uncertainty bands quite nicely like reflect this, that they are like widest by municipal rain gauges and are narrower by microwave lengths and narrowest by benchmark rain gauges. And at these hydrographs, you can also see an advantage of using microwave lengths, because with municipal rain gauges, we often have bad timing of this peak flow. With CMLs or benchmark rain gauges, we are able to capture this timing quite well. So microwave links can provide precise discharge predictions well calibrated to existing runoff data or rain gauges, and runoff model can be conveniently extended also by an error model and provide reliable uncertainty estimates. So just very few words to this like real-time model, which we did in the city of Olomouc. We're interested here if we can use just like attenuation data directly as an input to the rainfall runoffs without any conversion to rainfall intensity. So we can use it in a like data-driven manner, and if we are able to eliminate with this approach bias of microwave links. And we did it within a pilot project where the data was operationally delivered to the water utility of Olomouc in 2022. We selected 12 links while covering the catchments and without some erratic behavior. And we got from the municipality or from the water utility also runoff data at the wastewater treatment plant with time step of 30 seconds. So we had the runoff data to calibrate our model, and we developed data-driven attenuation runoff model to be like calibrated on this runoff data. And I will just show here two hydrographs. In red you see observations, in green this simulations, and you can see that we can like capture pretty well the peaks and timing of the peaks, and also to some extent volume, and the simulated runoff is very well in general like calibrated with the observed runoff, and we are able to predict this runoff in 1 hour like horizon before it comes to the wastewater treatment plant. So the simulated flow rates are in this case well correlated with measurements. There are pretty low systematic errors on average. So we conclude here that there is a considerable potential for operational runoff modeling. in a large urban catchments. The disadvantage is that we were not able to ensure sustainable long-term data availability for the municipality, and apparently some business models are missing to operate such models, and this is very like important for the water utilities, that they have a sustainable data flow, and that the system which is developed stays for several years at least. So to conclude, microwave link based runoff simulations capture very well rainfall temperature dynamics even without fine-tuning, but are often biased. These existing observations from rain gauges or flow meters can eliminate this bias even by relatively short microwave links, and real-time microwave link data can be conveniently used as an input for data-driven rainfall runoff models. But we lack some business models on how to run these models in long term. And our further research now concentrates on data-driven rainfall runoff modeling, automated quality control algorithms, rainfall spatial reconstruction at small scales, and also some methods for merging microwave links data with other observations. So thank you.
Thank you, Martin. It was a very nice overview what one can achieve using the CML data. Here is the question from George.
Yes, hello. So yes, this was really an interesting presentation. It's interesting for me because we exactly are in that domain. So there was nothing really new about it, but it's really interesting that this is done on other places, and also the kind of results that you can get with microwave links, because we are not yet on that level, because they are not available, or it's just not available information for us. But it is interesting to get this kind of feedback. But one element that I want just to also give you as a feedback is that you going from rain to the treatment plant. And so you're comparing the inflow of a treatment plant to the runoff or to the rain. But in between, you have the sewer system that has all kind of dynamic behavior, and it has also overflows. So it means that you are losing water, and this is not necessarily a few cubic meters, but it may be really a lot of water that you're missing on the way from the water drop that falls on the surface until it arrives at the treatment plant. There may be a lot of losses. And now your calibration that you're doing is including this calibration. So it's including the losses of water in the sewer system, not only the calibration of rain. So there is, and also not only the runoff. Right? So there is some items in your overall calibration that may be needed to be reviewed a little bit if you want to have the information of what is really arriving at the sewer system. I'm saying this because what we are doing is we are real-time controlling the sewer system. I mean, the flows in the sewer system, not at the treatment plant. And so what we are seeing is that in principle, internally in the sewer system, there's completely different flows than that you see at the treatment plant. So there's of course a correlation between them, but there's quite a lot of elements that take place internally in this whole modeling, or in the real world. I say it's because the model and the real world are not necessarily the same. That was just like a feedback from my side.
I mean, this is like very difficult to capture with data-driven modeling, where you don't have a data from the CSOs, but it is possible with deterministic models which are calibrated. And this, like a small catchment, it's separate sewer system, and there is no overflow. So at the outlet of this catchment, we really measure what is drained from the catchment, and this is sort of like simulating also with a size some subcatchment of one combined sewer overflow. So if you have a calibrated model, or if you want to calibrate model, and you have some like rainfall information from several rain gauges during this calibration, I think it's very convenient to complement them during the calibration also with microwave link. to capture
yeah.
better the space-time variability, but this needs to be done during calibration when you have also measurement at the CSO.
But most of the time you don't have that.
During
So
operation you don't have that, but during calibration of your model,
you also don't have it.
You should have it.
No, you don't have it. Most of the time, this information is really difficult to get. You may get an event information so that there is an overflow taking place, but the amount of water that overflows, you don't have it. It's not measured. It's also not in calibration data measured. So you may just get the event information. Yes, there's an overflow taking place, or no, there's no overflow taking place, but having the volume that was overflowing during an event is something that you will potentially not get. You may get it at one place because you specially do a measurement at that specific place, but this is really, really rare that you get this kind of information. And most of the time, the models that you have, even if they are called calibrated, they are far away from reality. At least this is our experience, that what we see in the modeling that we are comparing to what in real world is happening.
That's true. Therefore, we set up our own model in the case of this like experimental catchment to be sure that it's like very carefully calibrated. But I think, George, we will have to have some like separate discussion on this.
Yes, I agree.
Great. Is it any other question to Martin? Oh, it's the question in the chat from Christina. Dear Martin, thank you for the insightful presentation. I have a question regarding the collaboration established with the municipality and the water treatment plants. In this collaboration specific to the current case study, or have you managed to establish a long-term partnership for future studies and projects? Additionally, could you share how challenging it was to pitch the CML-based solution to the municipality?
With this in this case, I was like showing it was like it was like collaboration between us and T-Mobile, because T-Mobile was like and the water utility, and T-Mobile was like interested a bit if there is some like commercial potential, and we have quite like good contacts on water utilities, and in this case there was also some help of some like a project manager who was responsible for like application of our results. So he connected us with this like water utility. But as I said, we did not find the business models to run this, and the data flow was not sustainable enough to have a like long-term collaboration on an application level. And I think that this is challenging.
Okay, thank you. So now it's the time to introduce our second speaker.
Yeah, the other presentation will be presented by two speakers. First is Adriana Todorovic. She is an assistant professor affiliated at the University of Belgrade. Her main research interest is in hydrological modeling under changing and extreme hydroclimatic conditions and modeling with alternative datasets. Within the OpenSense action, she is a member of Working Group 3. And the other speaker is Greta Karadza. She is a postdoctoral researcher affiliated at the Paris-Saclay University. Her main research interest is in hydrological modeling, commercial microwave links, and modeling of extreme events. And within the OpenSense action, she is a member of 3 working groups: Working Group 3, Working Group 4, and 5. And with this said, the floor is yours, Adriana and Greta.
Thank you. I try to share the screen. Can you see right?
Yeah. full screen.
And can you hear me well?
Yeah, also.
Okay. I think that Adriana is going to start. Okay, so Adriana.
Yes, thank you. Good morning, everyone. Greta and I shall present you a piece of our, in a way, ongoing research on hydrological application of OS data, CML data in particular, and we shall present you the results that we got for the Lambro catchment in the north of Italy, which is perhaps one of the first attempts to use CML data to simulate runoff in one mesoscale peri-urban catchment. So let's start with reminding ourselves that hydrological models are essential for sustainable water resources management because they can give us information on values of hydrological variables where we don't have them, for example, flows at ungauged sites, or in the future when we talk about, for example, stream flow forecasting. They also can enable us to analyze various scenarios. For example, what would happen if we implemented some MBS, or what will happen under changing climate. Let's also emphasize that these models are often referred to as rainfall runoff models, which actually implies the importance of rainfall data on simulated hydrological variables. So rainfall depth, rainfall dynamics, and its spatial variability, we need all those pieces of information to accurately simulate hydrological variables, primarily flows. So in the next slide, we can see that rainfall data are traditionally being provided by monitoring network that include rain gauges. However, these observations are not uncertainty-free, to put it that way. For example, observations can be affected by the wind, then the number of gauges can decline over time, which is shown in the left-hand graph in the slide. Then we also know that the majority of these gauges are clustered at lower elevations. Then there could be issues with capturing the highest intensity rain events and so on. Therefore, over the past few decades, people started using radar and rainfall data and satellite rainfall data. But the thing here is they're not direct measurements. So, for example, if we use radar, we are actually gauging in a way reflexivity and try to infer rain depths from that information. From that information, which also poses some sort of uncertainty. So, in the next slide.
Yes, sorry, it's not working very well. Okay. Sorry.
Yeah, no worries.
Can you see? Next slide.
Yes, thank you. So we can conclude that obtaining rainfall data remains costly and still remains fraught with uncertainties, which actually provided an avenue for future research and development in application of OS data, which have a potential to provide us more information on rainfall and potentially to improve hydrological modeling. The OS data usually include personal weather stations, satellite microwave links, but here we will talk about commercial microwave links and application of these data in the Lambro catchment, and more about that case follows on the next slide.
Yeah, okay, here we just give you an overview of what we did in our project. The idea was to understanding which is the potential of using commercial microwave links, rainfall data retrieved from commercial microwave links for simulate the discharge in river in catchment that are rural or peri-urban catchments. So for doing this, we started obviously from the retrieved of the rainfall from the commercial microwave links, adapting the literature methodologies to our data set. Then we tried to validate the rainfall data against what we refer as benchmark, which are the weather station, the rain gauges data, both on a with a point-wise approach, but also at different spatial scales. So from the subcatchment to the catchment. Then we developed our own hydrological models, which could fit with the use of different rainfall inputs, so rain gauges, commercial microwave links, and radar as well. And finally, we validated the results, the simulations from that we got from this different type of rainfall data with our observation. And we did everything here in one specific catchment, which is the one that was introduced by Adriana, the Lambro catchment. Okay, on the left here you see all the data that in our research group were available. So we had some links over a mountainous region, and then more than 200 links over this peri-urban area, northern to Milano. And specifically, we started with looking at this red area, which includes the Lambro catchment. You can see it on the right. And here we had different measurements available. So the number of links was 50. We had also quite dense monitoring system of rainfall provided by the environmental agency of Lombardia, which is the region northern of Italy. We had 13 rain gauges, and then we use also data from the a radar that is in Swiss. So the data are provided by Meteo Swiss. Obviously, we needed other input data, and specifically temperature for the modeling of the hydrological modeling, and we could rely on 8 thermometers. And our observation come from an hydrometer, which is located in the outlet section of our hydrological basin, which is here. And okay, it gets the water level measurements, and then we transform with the rating curves into discharge. Here there's an overview of the typology of the rainfall data sets. The resolution of rain gauges, it's about 10 minutes with a quite good accuracy of 0.2 millimeters, and they are freely available. We could get for any year we want continuous data. So we use specifically 2.5 years for calibration and testing of the hydrological model. Then about the radar, we could rely on data from with a time resolution of 5 minutes and a quite good spatial resolution of 1 kilometer by 1 kilometer. They are available on demand. We paid probably a small fee for the data extraction from Meteo Swiss. And while for commercial microwave links, we had the mobile company in Italy, Vodafone, provided the data under a fee, and just for some specific events. In particular, we could rely just on 12 rain events, and the typology of data is minimum and maximum transmitted and received signal level every 15 minutes with a quite coarse resolution quantization of 1 dB, which we will see that could it's one of the main constraints that we have with this data set. Just a small overview of our algorithm for the retrieval rainfall, which is the one that also Martin presented. Just 2 main insights. The first one is that we calibrated the power law parameters, so K and alpha, since they typically depend on the hydrometers, the physics of the hydrometers. We use the hydrometers, so data from drop sites distribution of the rainfall to calibrate these 2 parameters. And then since we had to deal with the minimum and maximum values inside 15 minutes, we computed an unbiased estimator for getting the average of the rain intensity in these 15 minutes. So once we get the rainfall measure, the rainfall retrieved from the links, we compare them with the rain gauges. In this case, I just show you the comparison point-wise. So we select the links that covered our hydrological basins, and we compared with the nearby rain gauges. We also, among these 12 events, we divided them. We identified two main groups, high intensity event and low intensity event, and we can see that results are quite different with respect to the two categories. In fact, if we see on the left, we are comparing rain gauges rainfall accumulated over one event and the accumulated rainfall retrieved from the links, and we can see that the agreement is quite good. The regression line, which is the dotted line, is quite close to the bisector line. But if you look now at the low intensity event, here we can see completely different results, and specifically great underestimates for low intensity event. We can see also the regression line is even lower than the boundaries, which represent the 30% underestimation. And we observed that this was due to the lack of sensitivity of our links, so the coarse quantization. In fact, we observed that depending on the frequency and the length of our links, the minimum detectable rainfall rainfall intensity was between 1 millimeter per hour and 10 millimeters per hour. So there were cases, a lot of cases, in which low intensity events could have not been seen. And this is a great limitation of our data set. Now, just a few words on the hydrological model. We developed our model, which was a semi-distributed one. We subdivided the catchment into subcatchments or hydrological response units, and their behavior, the interaction among each HRU depends on the river network. So, for example, here we have catchment, subcatchment 1 and 2, which are in series with catchment 3. So this means that the outflow in 1 and 2 enters in 3. And here there's the water balance. So we had the measurement of precipitation. We computed all the inflow and influx and outfluxes. And the model can run on a continuous or event base with a time resolution of 1 hour. And we calibrated the model over 1 year of data. And our reference calibration was with rain gauges. So because we had continuous data, it was more difficult to calibrate data, obviously, with specifically with the links, because we had just 12 events. And once we have the model, we can think how to integrate the rainfall data in input in the hydrological model. And for doing this, we used quite a straightforward approach, the inverse distance weighting method, both for commercial microwave links and rain gauges. Specifically, links were considered as virtual rain gauges, so they were identified in their midpoint, and we for example, in this sub-basin, that since it's a semi-distributed hydrological model, we consider being homogeneously the input of rainfall, we consider it homogeneous over the entire basin. We select the centroid and of the basin, and we select all the measurements that are inside a radius of 10 kilometers. We do the same thing for rain gauges and virtual rain gauges. So the links, while we also try to use radar data. And in this case, since we have gridded data, we just computed the average over the pixels that are inside our HRU. Here, once we have our data that are aggregated on the subcatchment scale, we can also observe compare results of the rainfall measurements on the subcatchment scale. And here we just have an example for one specific event, event 3, which is a high intensity event. We can observe that the colors of rain gauges and links and the combination of the two for each HRU is quite similar in the 3 cases. But for the radar, we observe a great underestimate in all the subcatchments, and actually we could observe that the problem was due to the fact that the radar was installed in Switzerland, and we have the Alps between the catchment and Switzerland, and this could have created problem in observing the rainfall intensity. If we look at a specific time series for one HRU and a specific event, here we have again event number 3, we can observe that links and rain gauges, so blue and green, are quite links quite well represent the dynamic and the peaks of the rainfall event, same for event number 7, while the radar, in this case, this event 3, doesn't observe the peak, and in the event 7, it also is also unable to capture the rainfall dynamics. Now we have done a comparison, the rainfall measurements. Adriana will continue with the comparison on the discharge simulated with our hydrological model.
Exactly. We use the reference model that Greta has just described and all these different sources of rainfall to simulate runoff at the outlet of the Lambro catchment. So on the left-hand side, we can see simulated hydrographs versus the observation, which is this dashed black line during the event number 2. So we can see that the rain gauge data and the CML data and their combination result in the runoff that is rather close to the observation, whereas the radar data resulted in a way off hydrograph. This is one example, but on the other hand, we have simulation results with a reference model during the event number 5, where we can see larger discrepancies across different rainfall input data. So these discrepancies translate further on the performance measures, which are shown in the next slide. So on the right-hand side, we can see Pearson correlation coefficient. So we are talking about the simulated hydrographs versus the observations. So we can see a lot of dark blue shades, which indicates high correlation, and that runoff dynamics is quite well captured, except for the radar to some extent. But if we have a look at the Nash-Sutcliffe coefficients on the left-hand side, we can see a lot of green and yellow shades in this panel, which indicate even negative values of Nash-Sutcliffe, which is unacceptable. So in some cases, apparently, we still have that the radar data is outperformed by all other rainfall data. But we also have large variability across the remaining 3 data sources. So, for example, in the event number 2, we have pretty high Nash-Sutcliffe values. In the event number 8, we have quite good performance with rain gauge data, whereas CMLs do not capture that, even though they result in quite high correlation with the observed flows. And in some events, such as the event number 12, we have simply poor performance everywhere. In some cases, it is really difficult to disentangle, like what caused exactly these low values of Nash-Sutcliffe. So in the next slide, we presented bias in simulated runoff volume, which is the upper left-hand panel, and relative errors in the peaks. So ideally, all these lines, which indicate simulations with reference models and different data sources, ideally, they should be as close to the thick black line, which is 0, as close as possible. So what we can see, we have the closest to this thick black line is actually the blue line, which shows the results obtained with the rain gauge, which it comes as no surprise because the model was calibrated with the rain gauge data. When we talk about VR or CML data, we see that in some instances we have overestimation. And in some instances, such as event number 7, we have underestimation both of runoff volume and runoff peak. And we have really pronounced underestimation of both variables when we use radar data. So apparently no systematic error. But what we can conclude from this is if we have a look at the right-hand side panels, these errors could not be linked with the maximum intensity over the rain event, which in a way could be considered as a proxy for the event severity. So in the next slide, we also did show some other results with some other analysis that we conducted. So in both panels, we have performance of the reference model, which is the top row. Left-hand side is Nash-Sutcliffe and the right-hand side is Pearson correlation coefficient. But the remaining rows actually show the model that is calibrated with the rain gauge data, automatically calibrated with the rain gauge data, with the CML data, their combination, and with the radar data. So we developed additional models which are optimized according to these alternative, in a way, data sources. And we now show their performance not only with their respective rainfall data, so the data that was used for their calibration, but also we decided to analyze transferability with respect to application of different rainfall data. So once again, what really strikes our eyes is really lower performance by the radar model. So different rows indicate different models, whereas different columns indicate different input data. We have a lot of dark blue shades in both panels when we use rain gauge data, and slightly paler blue shades when we use CML data with all models, which actually indicates that might indicate that the rainfall data captured by CMLs has some bias, which is indicated by the fact that Pearson correlation is high and Nash-Sutcliffe is slightly lower. But we also should remind ourselves that these performance indicators are obtained over all 12 events combined. So in the next slide, we really have just one specific event, which is notorious event number 8, where CML data couldn't have captured runoff volume. They did runoff dynamics, but not runoff volume, which actually shows quite significant bias in terms of simulated runoff volume and also relative error in peak. And once again, we can still see that if we use radar data, which is indicated by the fourth column in both panels, we usually end up with underestimated both runoff volume and runoff peak. So in conclusion,
about the validation of rainfall measurements, we observed that there was a good accordance between Link's dataset and the rain gauges. With respect to high-intensity events, we observe this lack of sensibility of the links with respect to the low rain rates. While with respect to the radar, we observe that this does not seem to that can be used properly to simulate the reverse discharge in this specific catchment, as it underestimates a lot with respect to rain gauges and commercial microwave leaks.
We also saw that we can have quite high model performance with using CML data. solely or combined with the rain gauge data. However, we also demonstrated that we have a large variability across the rainfall events. And our research also shows really, really limited transferability of models with respect to the rainfall data that we use. So which indicates that if we want to use CML data for hydrological modeling, then we should take that into account and develop our models with that kind of data. And with these conclusions, we would like to thank you for your attention.
Thank you very much, Greta and Andriana. Is there any question from the audience? Yeah, the question from George.
Yes, I don't want to always ask questions, but if nobody else asks questions, I try then to just ask a question. So one element that strikes me is that you have this variability of the events according to the runoff. And I think, I'm not sure, because we see this on urban areas, that there's a large impact on humidity. So depending on how humid the soil is, or how humid also the history of humidity, the runoff is completely different. And I can imagine that on natural areas, this is similar. So maybe you need to add additional data to your modeling to better capture the runoff behavior based on additional data, not only the rain.
Thank you for your question. This is this is a really, really valid question. We are all aware that initial conditions are really important for simulated runoff. What we did here is that we, in a way, used continuous modeling with the rain gauge data to set the initial conditions. So in a way, we consider that we captured as much as possible those initial conditions. The model is really robust with respect to simulation of soil moisture. And so hopefully we did at this point as the best we could. And as for application of some soil moisture observations, I have to forward that question to Greta, because I'm not aware if those data are available for this catchment.
Yeah, probably they're not. I'm not sure. There's also I saw Alessandro Ciappi, who works on this catchment for a lot of time, so maybe he's more aware. But yes, probably also moving from a semi-distributed hydrological model to a distributed one, which requires more computation and so on. But this for sure would improve the simulation and simulation of soil moisture as well, I think.
Thank you.
I think that another question is from Thomas. Thomas, do you like to ask the question? Okay, I don't hear you, Thomas, but if you want to ask the question, then you can write it in the chat or
okay,
or
sorry.
okay.
I was just interrupted by a phone call, and so I could not continue. I have a question. You may know that I am working quite a bit with radar data, and I have, well, two questions on the radar data. You said they are from Switzerland, so maybe Montelema, and maybe another radar. So what is the distance between your catchment and the radar? And the second question is, do you know if the radar data have been adjusted to Italian station data?
Maybe I answer, but I'm not into radar. So, and I really didn't work on it. So, at the distance, I think that I don't know how to answer to both of the question.
Mm-hmm.
And yeah, no, maybe Roberto, but I'm not sure about this. If he wants to jump in the conversation, he can provide you with more information.
No, because
No, okay.
because if, well, in former days when we worked together with Meteo Swiss over some catchments in Italy, there was no ground comparison to a station data, and this means that automatically you do not have a good quality of the radar data, in particular if you are further away than 100 kilometers from the radar.
Yeah, I don't think we cannot be farther away than 100 kilometers. Yes, but yes. Yeah,
and,
so it's this. Yeah, it was the only radar that was available for us. So we did a trial, but probably yes, it was not also calibrated with ground truth there. I would say.
If you want better results, then you should probably post-process the radar data before using them.
Yeah. Okay. Thank you.
But we can talk about that on the side if you like, and we are planning to work with Meteo Swiss data later this year, so in autumn, and so I will be in direct contact also with the guys from Meteo Swiss.
Yeah. Okay. Perfect. I think that Roberto Nebuloni was in contact with them, so maybe we can have a chat and.
Yeah.
Okay. Thanks. Thank you.
Thank you too.
Okay, great. So we have time for the last question. It's the question asked by Christina in chat. Thank you, Adriana and Greta. Do you expect that you could get better performance of the model with availability of more rainfall events available?
Well, you never know, because in some cases, the more events you add, then in some cases you can get worse performance or better. That heavily depends on the event, like we showed. But regardless of the model performance, I can say that the more robust models and more robust conclusions we will get about the applicability of CML data. That's for sure. And that is definitely needed to improve our model, because we had really limited length of the data series, like Greta said. So we really believe that additional data will help us to improve and make more robust our model and our conclusion.
The constraint I would add here is the relation with the mobile company. So there seems that they're not so responsive and collaborative. So it will be difficult to get more data, I would say.
Great. So thank you for all the answers, and thank you the audience for being active. I see that there is also another question from Kumar now. Okay, I see that you are talking in the chat. That's great. And with this, I want to thank all of you, our speakers today, and also the whole audience that you joined the conference during this holiday time. And I wish you a nice day. Thank you.